Hello, I'm Mr. Bob, and welcome to my Geometry Review video series. This video covers Chapter 11, Section 2, titled Chords and Arcs. By the end of this video, you will have reviewed recent lessons describing chords and arcs. Discussions will include using congruent chords, arcs, and central angles. You will review the use of Theorem 11.4 and the proof of Theorem 11.5 from your textbooks, and then you'll use it. Additionally, you will review theorems related to lines running through the center of a circle, and then review the use of diameters and chords. If you would like me to cover any of these topics in greater detail, please leave your request in the comment section below. Please subscribe to this channel if you find the video helpful. Thank you. Okay, let's start by looking at a definition. So what is a chord? A chord is a segment whose endpoints are on a circle, and it is called a chord. So anytime we have a segment connecting across the circle somehow, the endpoints of this segment on the circle, we call it a chord. Okay, objective 1, we'll call it 1A because there are more slides to this. Objective 1, using congruent chords, arcs, and central angles. To remind us again, a segment whose endpoints are on a circle is called a chord. The diagram at the right shows the related chord and arc, PQ, the chord PQ, and the arc PQ, respectively. So what we're saying here is that right now when you look at this, where's my pencil? There it is, that this chord right here going through the circle right here, this chord from here to here, is named the same as the arc about the circle right here, PQ. And those are the two we're talking about. The following theorem is about related central angles, chords, and arcs. It says, for example, that if two central angles in a circle are congruent, then so are the two chords and arcs. The angles intercept. Very interesting. So let's look at the theorem. Theorem 11-4. Within a circle or in congruent circles, congruent central angles have congruent chords. Congruent chords have congruent arcs, and congruent arcs have congruent central angles. So you see it's like a circular thing going on, right? One leads to the next, and they're all the same. And what is a central angle? A central angle, if I can draw it, would go from here to the center there, and then from Q the same way, it would go here. So this is the central angle right here. And that central angle the endpoints end up on the circle, and those 2 points, from those 2 points you can stretch a chord, or the arc is outlined. That's the central angle. So this congruent central angles have congruent chords and arcs, and vice versa. If you have a congruent arcs, then you also have congruent chords and congruent central angles. 11.4 is pretty powerful. Okay, example 1, using Theorem 11.4. So it says in a diagram, on the right, you see two circles. You see, what do we see? We see circles, we see chords, we see arcs, and we see central angles. So in the diagram, circle O is congruent to circle P. So they're telling us right now these two circles are congruent. Given that arc BC is the blue part right here, arc BC, where's my pencil? The arc BC along here is congruent to arc DF. There's arc DF. And it says given. They're telling us that they're equal, that they're congruent. What can you conclude? Well, from 11-4, 2 and 3 for sure, those two and 3, angle 0 or angle O is congruent to angle P. Angle O is this angle right here. And angle P, these are central angles. They are congruent because it said that congruent arcs have congruent central angles. And B and C, BC is congruent. BC, which is going from B here Now we're talking about the segment, or the chord, and DF. They're congruent because congruent central angles have congruent chords. It's kind of a, like we were talking about, it's a little bit of a round robin sort of a thing. Okay, so that's what we concluded. Now, so if you are instead given that BC, the chord BC, we'll draw that one here, the chord BC goes right from here, is congruent to chord DF, what can you conclude? Well, we can conclude the exact same things. From 11-4, we can conclude that congruent chords have congruent arcs. Congruent chords have congruent arcs. Chords have congruent arcs, and congruent arcs have congruent central angles. Congruent chords, congruent arcs, and congruent central angles. Look at that picture. You'll be seeing that and needing it as we move forward through our lessons and our reviews. Okay? Good. Okay, Objective 1B. It's the next slide in Objective 1. Using congruent chords, arcs, and central angles. We're still talking about angles and arcs and central angles and chords that are all congruent. Within a circle or within congruent circles. So within a circle right here, within a circle or in congruent circles, chords equidistant from the center are congruent, and chords and congruent chords are equidistant from the center. I think we'll see a picture of that in the next slide, but this is also very important. So try to remember these as we move forward. Okay, in Objective 1C, the third slide of Objective 1, using congruent chords, arcs, and central angles, we're going to attempt the proof. The proof is in front of us. We'll read it. There's a lot of words here, and it may be hard to follow, but just take our time. We'll try to say everything that needs to be said here, and then you can always repeat this 2 or 3 times until it sinks in. But really, we're just proving it. But it's good to see the proof, because seeing the proof shows you all the pieces that you will use in the future when you're solving problems. All these little pieces that we're putting together will form a larger picture in your mind when you're solving problems. But let's give it a try. So it says, given circle O, you see circle O right there, the O is in the middle of the circle. You're given that, you're given the circle, and we're given that segment, or what is it, OE? OE, that segment AB, OE is congruent to OF. So there, and you see it, right? There's a little dash on here, right? The little dash right there. There's a dash here and a dash here. They're saying that these are congruent. Those are congruent. They're telling us that. And OE is perpendicular to AB. So this little segment OE right here, OE is perpendicular right there to AB, and the same for the other side, that OF is perpendicular to CD. So that's the given facts. Now prove that AB, now this is chord AB, or segment AB, is congruent with CD. So what do we know? We know that the small segments in the center here, going from the center of the circle to the chord, are congruent. We know there's 90-degree angles. So we've kind of established that. So what does it say here? It says OA is congruent to OB. OA, okay, OA is a radius. OA and OB and OD and OC, they're all right here. OA, OB, OC, OD are all congruent because they are radii of the circle. Okay. OE is congruent to OF. They already told us that. It's given. And OE is perpendicular to AB, and OF is perpendicular to CD. That's the given stuff we read earlier. This stuff up here. So then they're saying angle AEO, I'll write it in maybe blue. Hopefully we can get blue. Come on, blue. AEO. So that's that angle there. And CFO, that you see the angle. I'm kind of circling around it there. CFO are right angles because we were told and given the fact that they're perpendicular, and the definition of perpendicular segments mean it's 90 degrees, right? They're right angles. A triangle AEO is congruent to triangle CFO. So now they're saying that AEO, that this little triangle right in here, is congruent to this triangle that's in where this dot is held in, and that's by the hypotenuse leg theorem, right? It says that if you have a hypotenuse and a leg that are congruent, then the third leg in that triangle is also congruent. Okay, so and that the triangles are congruent. So AEO is congruent to CFO, and angle A is congruent to C. A, we know that angle A is right out here. This is angle A, and angle C, that they're congruent because these are congruent triangles. These triangles are congruent to each other. Okay, we've said that. We've proved that already. And A is congruent to C because of corresponding parts of congruent triangles are congruent. So these angle C and angle A are corresponding. Okay, because they're not here at the 90 degree, and they're not up here at the vertex at the center of this circle. So these are corresponding parts of corresponding triangle. Corresponding parts of congruent triangles are congruent. I think that's the wording. Then angle B is congruent to angle A. Okay, angle B. Angle B is congruent to angle A because of the isosceles triangle theorem, because these are isosceles triangles. Okay, these two common legs here, and so this is an isosceles triangle, and the opposite triangle is also. What does it say? Does it say and angle C and D? C and D are also congruent because they're equal congruent angles in an isosceles triangle. Angle B and angle D, that's the angles over here on this side now, B and D, they are congruent because of the transitive property of congruence, which says that you have congruent these parts are congruent over here in this triangle, and these triangles are congruent now, so these parts are also congruent because of the transitive property of congruence. So, and then if angle AOB is congruent to angle AOD, if two angles of a triangle are congruent to two angles of another triangle, then the third angles are congruent. That's kind of like what we were talking about, the transitive property. That one equals the other, right? If these are equal or congruent, then the other is also congruent. Basically what that's attempting to say there, I think. These proofs are hard to read through sometimes. Then finally at the end, if these are all congruent, then that's telling us then that AB and CD are congruent. That's what we're looking to prove, because central angles have congruent chords. So this angle, since these angles here of the isosceles triangles, oops, there's that line again, that makes this a central angle, and these central angles are congruent. These are two congruent isosceles triangle. We know the outside angles are congruent. Then these central angles are congruent, and central angles create central chords and central arcs. So therefore, AB and CD are congruent. Okay, example 2, using theorem 11-5. Find the value of A in the circle. So you see the diagram there. A is right there. You see it on that chord. It's attached at 90 degrees to that chord. So what are we saying here? PQ equals to QR is equal to 12.5. This is given information. PQ equals QR, and those are given that they are equal because it shows right here what the dashed lines right here. They're kind of indicating that with these dashed lines right here, that these are congruent. So we know that that those are congruent, that those are the same. So PQ plus QR is equal to PR, right? So that must mean that through segment addition, the segment addition postulate that says that if this segment here is congruent to that segment or equal, then the sum of them, okay, we can add those and come up with a size. And we now know that 25 is PR because we can say 12.5 plus 12.5 is 25. So by substitution, we have right here that PR is equal to 25. So given PR is equal to 25, A is equal to PR because what did 11.5 say? 11.5 said chords equidistant from the center of a circle are congruent. Well, how do we know they're congruent? And how do we know they're equidistant from the center? Because it tells us right here. They're both 9 inches right here. These two are 9 inches each. So they are each equidistant from the center of the circle. So if they're equidistant from the center of the circle, they're congruent, right? It says chords equidistant from the center of the circle are congruent. Well, if the chords are congruent, then they're equal to each other. So substituting A to equal 25, we now have the size of A, which is 25, because we know that PR is 25. So A then must be 25 because we've proved that the PR and this segment A are equidistant from the center using 11.5. Okay, example 2, checking your understanding. So what they want you to do is to stop the video. I think you should stop it and try it on your own. And then when you come back, we'll work it together. So go ahead and stop. I'll wait for you. Okay, I'm assuming you've done that and you're out your back. So let's take a look at it. It says, find the value of X in the circle. Well, they don't give us much. There's no points, no A's, no B's. And I don't think it's necessary to write all that in. Let's just talk about it in general terms. But we know that due to 11-5, we're going to be looking at chords and equidistant from the center, this type of stuff. That's what 11 does, 11.5. So we're going to see right off the bat that we have a chord that is made up of 2 segments. And do the segment addition postulate, we're allowed to add these together. So we're going to go ahead and say 18 plus 18 is equal to 36. Okay, and we also see in here that we have 2 chords, the 18 plus 18 chord, and then there's a chord that's 36. So we also know that chords that are 36 equals 36, if they're the same, if the chords are congruent, then they are equidistant from 11.5. They're equidistant from the center. Well, that tells us that this chord that is stated as 36, whatever units long, is the same distance from the center of the circle as the one with the 2 segments of 18. So we do know one thing. We know that the distance from the previous, the 18 plus 18 segment, is 16, right here, 16 units from the center. And since these are congruent chords, the distance, they're equidistant from the center of the circle. So that makes X equal to 16. Okay, objective 2a. So we have objective 2 is going to have 2 slides. So lines through the center of a circle. That's what it was called. So the converse of the perpendicular bisector theorem has a special application to a circle and its diameters, chords, and arcs. So let's look at theorem 11.6, 11.7, and 11.8. 11.6 says, in a circle, a diameter that is perpendicular to a chord bisects the chord and its arcs. So if it's perpendicular to it, it's bisecting the chord and the arc associated with it. Theorem 11.7 says, in a circle, a diameter that bisects a chord that is not a diameter is perpendicular to the chord. So now we know that it bisects it and it's also perpendicular to it. And thirdly, 11.8 says, in a circle, a perpendicular bisector of a chord contains the center of the circle. So that's if you have a circle, like what do? We got to draw. It's kind of, if you draw on a circle like this, and we've got a chord here, and you've got a diameter, right? So what does it say? A perpendicular bisector contains the circle. So if you come off of this, isn't actually perpendicular, is it? But if you come out, you're going to go through. I should have drawn this circle bigger. Maybe I'll draw it bigger. Let me see if I can draw it bigger. That's not letting me switch. There we go. Okay. I'm going to go outside the box. It'll be bigger and better, I think. If I have a circle like this, not a very good circle, however, here's my chord, and here's the center of the circle. You've got a perpendicular bisector. This runs right through. It contains the center. So that's what they're basically trying to tell you here, okay? So a diameter that is perpendicular to a chord bisects the chord. So if this is 45 degrees right here, or 90 degrees rather, 90 degrees, that means it's perpendicular. And if it's perpendicular, it's bisecting the chord. It also bisects the arc. The diameter that bisects the chord that is not a diameter that bisects a chord that is not a diameter is perpendicular to the chord. Well, now we know that it's saying if these two halves are congruent, then we know this must be the bisector, perpendicular bisector. Okay? Okay, objective 2, lines through the center of a circle. Proof of theorem 11.7. Given circle T with diameter QR bisecting SU at V. So I think we can see that. QR is the diameter, SU is a chord, V is the point that it's being bisected at point V. And it says prove that QR is perpendicular to SU. So reading through the proof, we'll go slow and see if we can make sense of it here. TS equals TU. So those are the radius, 2 radii of the circle, going from point T, one to S and the other one out to U, because the radii of a circle are congruent. VS equals VU. VS, okay, that's from the center of the circle right here. VS equals VU. By the definition of bisects, early on the top in the given, it says it bisects. Thus, T and V are equidistant from S and U. T and V, well, T is the radius distance to S and U, and V is the bisected distance along this chord, and they're equal. Everything here is equal, right? They're congruent pieces. VU and VS are congruent, and TU and TS are also congruent. It says by converse of the perpendicular bisector theorem, T and V are on the perpendicular bisector. T and V are both points that are on QR, which is the perpendicular bisector of SU. And since the 2 points determine one line, any 2 points determine one line, TV is the perpendicular bisector. We can say TV then is therefore the perpendicular, I'll draw that. TV is right here, this little piece right here. Perpendicular bisector of SU. And another name for TV, since you can have as many points on a line as you would like, they're saying you can name it anything you want, but QR are points, Q and R are points on TV, the line TV extended. So it says TV is the perpendicular bisector of SU. Another name for it is TV is QR. Thus QR is perpendicular to SU. That was fun. Okay, example 3, using diameters and chords. Find each missing length to the nearest tenth. So what we're looking at here, the missing length in problem A is the N. Oh no, I'm sorry. It's R, okay? And in B, the missing length is Y, right? CB, but it's a different portion of this triangle. So in order to look at that, we're going to say, well, it says LN, right here, going across this segment right here, I'm going to LN, right here, is half 14, right? We know that this perpendicular bisector right here, this perpendicular, it says it's perpendicular bisector, excuse that, my pencil sometimes goes weird on me. Look at it, going all over the place. So I got to erase that. Sorry. I don't know why it does that. Anyways, so LM is 14. It tells us that it's 14 centimeters, and we want half of it because this is a perpendicular bisector. So the segment from L to N is 7. And now we can use the Pythagorean theorem, which says that R squared, we're looking for the hypotenuse out there. R is the hypotenuse, the side opposite the 90-degree angle, is equal to 3 squared plus 7 squared. 3 squared plus 7 squared. So R squared is equal to 9 plus 49. And R squared then is equal to 58. Right here, 58. And 58, we're taking the square root of both sides, is equal to 7.6. I guess approximately, probably, but 7.6. If we go to the next one, B, we're going to have BC is perpendicular to AC. Okay, BC, right here, this little segment going from the radius, from the center rather, to intersecting the segment is perpendicular to AC, which is, as you see it here on the outside. Again, using the Pythagorean theorem, y squared, which is, in this case, 15, the hypotenuse is 15, okay, is equal to 11 squared plus y squared. So we have y squared plus 11 squared is equal to 15 squared. We have y squared is equal to 15 squared minus 11 because we moved the plus 11 squared from the left side to the right side by subtracting 11 squared from each side. So now the 11 squared is on the right-hand side. So now we can say y squared is equal to 225, 15 squared, minus 121, 11 squared. Okay, and then y squared is equal to 104. That's the difference between 225 and 121. The square root of both gives us y is approximately equal to 10.2. In this case, we can't say centimeters on the bottom because it doesn't say centimeters. On the top, I guess we could have put centimeters. In here, I can write right here, centimeters. Oops, centimeters right there. Okay, good. Okay, example 3, check your understanding. They would like you to use the circle at the right to A, find the length of the chord. The chord is X, is the length is the chord. And B, find the distance from the midpoint of the chord to the midpoint of its minor arc. Well, what is its minor arc? The minor arc is this arc from where my pencil go. There it is. The minor arc is the arc from here. I'm just going to draw around here. This is the minor arc. Oops, sorry. The major arc would be, and I'll just kind of loosely draw it, it would be this piece up here. This would be the major arc. I'm surprised I got around there that well. Anyway, so the major arc, they don't want to know the distance from to the major arc, the center of it. They want to know the distance to the minor arc. So go ahead and try these on your own. When you come back, we'll look at it together. Okay, so now you're back and ready to look at this. So it says find the length of the chord. Well, what we know is from Pythagorean is the theorem that we have the radius is 6.8, and we have a leg of a right triangle. We see it's a right triangle of 4. So we're really going to have to find the other leg, right? And that other leg is 1/2 of x. So we're looking right now. We're going to look for 1/2 of x by taking what 6.8 squared, and that's going to be minus 4 squared, and that's going to be equal to, well, I'm just going to write 1/2 x squared. Okay, mathematically it might not be exactly like this, but this is to get the idea. So 6.8 squared ends up being 46.24. 46.24. And we know minus 16. We know that that's 4 squared is 16. So we're going to get 30.24. That equals 30.24. So now, if we take the square root of both sides, right? So we're going to get 30 right over here. We're going to get 30.24, the square root of that, and the square root of our 1/2 x value, right? So that's going to give us, what is that going to give us? It's going to give us a square root of 30.4 is going to be 5.5. So 5.5 is equal to 1/2 of x. So we need all of x. So all of x is 5.5 times 2. So x is going to be equal to 2 times 5.5. Okay, and that's going to be equal to 11. And I'm going to say it's going to be approximately equal to 11. Okay, and that'll be close enough, 11. And then find the distance from the midpoint of the chord to the midpoint of its minor arc. Well, we talked about the minor arc. That's this section down here. I'm going to change colors so we can see it more clearly. That's this section down here, right? This is the minor arc. And they want to know that to the right here, to the midpoint of the minor arc. Well, how do we do that? Well, we know the distance from the center of the circle to the chord is 4. Well, we also know that the radius is 6.8. Well, if you could bring this radius all the way down, the radius would come all the way down here, right? Oh, that's the radius. So if you take 6.8, down here, 6.8 minus 4, you're going to end up with 2.8. And that's going to be the difference. It'll be 2.8, whatever it is, inches or miles or whatever. Do you get that? See it? Okay, good.